In previous lectures, we talked about the magnetic force on a charged particle. So if we imagine we had some sort of a particle, as we do right here, and if it were just sitting in a magnetic field of constant strength, we know that actually there would be no magnetic force acting on the particle, since, as we learned, that the magnetic force is the product of the cross product between the velocity vector and the magnetic force, or magnetic field vector. So if there is no velocity, then the particle is not going to experience any force on it at all. Now, if instead, let's imagine there was some sort of a velocity vector there, then if we apply the right-hand rule, we would expect that there would be a force acting on that particle, and to be acting downward along this way, with the magnetic field going into the screen here. Now, if this were the case with the velocity going that way and the particle moving about, then we'd expect it to basically just start going in circles of some form, like so. In that case, then, if it were just going in circles, it would actually have constant velocity, no work would be done on the particle, that sort of thing. But if we were to imagine, instead, that this particle was actually in some sort of wire, then again, if the whole wire has some sort of velocity forward, there'd be a downward force from the magnetic field. And so instead of going in a circle, it would just go straight down along the wire. In that case, what we'd have is we'd have moving charged particles along a straight path. We'd have a current. So we've already figured out some way then of having, say, a magnetic field producing a current, somehow forcing a current to come along. Now, instead of having some sort of a charged object or some object that has electric charges in it moving through a magnetic field, let's have some sort of a loop or ring static in our frame, and then let's actually move a magnetic substance or magnetic object across, in this case just a simple bar magnet. So if I were just to hold that bar magnet in place, I would expect nothing to happen. Why? Again, because there's nothing moving relative to the magnet, or the magnet's not moving relative to the ring here, so you'd expect there to be no magnetic field or magnetic force acting on anything. But instead, though, if we suppose that there's some sort of a velocity vector, then we would actually start expecting there to be the same sort of situation of some sort of a current moving through the wire. And if we hook this up to some sort of ammeter, something to measure the current going through, we'd actually see there is some sort of current. And also the direction of that current is going to matter whether I have this magnet moving to the left or to the right. So this is telling us then that even moving a magnet can produce the necessary force to produce some sort of a current. So to explain this, the law that we try to use is going to deal with two particular things. One is related to what is the magnetic field, what the magnetic field is going through, and how fast things are changing. So part of this we're going to need to use our definition of flux, and this time for magnetic fields. So this is the same sort of concept we had when it came to flux with electric fields that depended on the magnitude of the field. It's going to also depend on the area that we're going through, and we're going to put this into a vector form and having an integral form as well, because we might have a more odd shape of things for the magnetic field to go through. So this is the most complete form to talk about the flux. So given this definition of flux and the observations that have been made about how either having something moving through a magnetic field or moving a magnet itself, somehow changing the magnetic field, its orientation, its strength, that sort of thing. The law that we attribute to Michael Faraday is this, that if you have a changing magnetic flux with time, that is going to actually induce an electromotive force. There's going to be some sort of a potential difference created by changing the magnetic flux. And there's usually also a minus sign here as well. Why is that the case? In part, you can imagine that as a response to what's going on. When the magnet is moving in one direction, it's going to try to produce a current through there. The current itself is then going to be a response to that magnetic field force. It's being pushed, so from Newton's third law, you'd expect some sort of a push back. So one of the things you're also going to notice is if you push a magnet through some sort of a coil, you're actually going to notice there's resistance against you. So that minus sign is in many ways very much trying to tell you about Newton's third law acting back on you in this case. So according to this law, let's see what sorts of things that it's supposed to apply to us. For simplicity, let's assume we just have some sort of simple loop of some sort, say, a square loop that we have. So we have constant area and so this will make our integral a little bit easier. And so I'm taking a negative time derivative of the b dot surface area vector. So we have negative time derivative of magnitude of the B field, surface area, the size of the loop we have, and the angle between the loop and the magnetic field. So according to this equation, if we were to change the strength of the magnetic field, we would get an induced EMF. If we were to change the size of the loop, we would get an induced EMF. And even if we change this angle, we'd get an induced EMF. So if I were to rotate the loop with respect to the magnetic field, then I could actually get an induced EMF. I could actually get some sort of potential out of just rotating this sort of thing. If I were to somehow change its size, I could do that. And if I were to change the strength of the field or move the loop around to some place where the field is getting weaker or stronger, then I'm going to get an induced EMF. And that's the interesting thing too. It doesn't matter if you're making the B field stronger or weaker, you would still get the same magnitude just by the rate of change of the magnetic field strength. Now, of course, if you're making the B field stronger with time, then that's going to make this a larger negative value. So the direction that you'd be causing a potential difference would depend on if you're going from stronger to weaker magnetic field. But whether you're going to stronger or weaker to stronger, only thing that matters is how fast you're changing that, not if you are going to stronger or weaker. You'll still get just as big of a potential difference. And of course, since we know that there is a relationship between the potential difference that this causes and, say, the current, since we know that delta V equals IR, then depending on how much resistance there is and the substance we're using for a particular, let's say if we're talking about the loop itself, if it's made out of copper, then you'd have some sort of current moving through the copper loop. And depending on what the resistance of copper is, which is fairly low, that would tell you then something about the current, depending on how big of a induced EMF you're using, how much of a potential difference you're causing by changing the magnetic field or changing the orientation of the loop to the magnetic field, etc.